Okay, thank you for the introduction. Thank you for this award, both on behalf of myself and on behalf of my colleagues who are not physically here. It's truly an honor for us receiving this important recognition, and I'm also really grateful to have the chance to share the results of our research in such a beautiful place, so thanks again. The title of our study is, as already mentioned, integrating a BIM-based path planning with audio augmented reality navigation assistant for blind and visually impaired people. And what I'm talking about is the introduction and the scope of the study. I will present related works and existing technologies that guided us to define the methodology we applied to develop the system proposed in this study. Then I will present the experiments we conducted to test the effectiveness of the proposed system. And finally, I will wrap up with some conclusions related to the conducted experiments. Before going to the core of the research, I would like to quickly introduce myself. I'm Leonardo Messi, researcher from Università Polytechnic delle Marche, based in Ancona, Italy. I've been working in the built environment production and management research group since 2017, and since then my research topic is related to digitalization of the construction industry, with a specific focus on digital twins and immersive technologies like, for example, augmented, mixed, and virtual reality. I focused in particular in this domain on the automatic registration of augmented reality, and I applied this knowledge to develop the system I'm going to present. This study is framed within the Vitality project. As you can see the logo in these slides. The Vitality project is proposing innovative solutions for people-centered sustainable buildings. So this is the topic related to our study. So I would like to start this presentation inviting you to imagine entering a complex building for the first time without having the chance to see what is happening around you. So let's suppose you have to go from point A to point B in a complex building, and you can understand how this can be challenging, especially if you are in that building for the first time. Well, this is what affects millions of people in the world affected by blindness and visual impairment. In fact, according to the World Health Organization statistics, in the world there are more than 280 million people affected by visual impairment, and unfortunately this trend is expected to grow up fastly in next decades. So there is the need to develop navigation assistance for blinds, and according to the state of the art, existing solutions can be classified into electronic travel aids that basically support obstacle detection, and electronic orientation aids that support navigation and orientation. In this study, we focus on the second group, so on electronic orientation aids, and I would like to briefly introduce what such a system can do. It supports orientation, so answer the question, where I am. It is possible by providing the user tracking task, and the other important task is navigation, so answer the question, how do I get there? So how do I reach the desired destination? This is possible by addressing two important tasks that are path planning and path following. According to the state of the art, what is missing is proposing a navigation assistant for blinds that can work in mixed and prepared environments, so that can work indoors, outdoors, without the need to install any physical infrastructure. And according to this requirement that we fix to provide a solution that can contribute to the state of the art, we studied the existing technologies related to user tracking and path planning, leaving apart the path following that is more related to the user behavior. Instead, user tracking and path planning are more related to the system design. So we collected existing technologies into this big taxonomy I would like to start with the user tracking. Existing studies can be classified into non-vision-based and vision-based solutions. Among the non-vision-based solutions, we have a lot of sensor-based approaches that requires the preparation of the environment, so requires installing sensors to track the user. In addition, some solutions are affected by high installation cost or short operating distance or low accuracy. Some of these issues affects also some technologies in the vision-based group, for example, IP camera and RGBD SLAM. And so this is why we notice that the solution that do not require any kind of physical installation is the ones based on computer vision, so structure from motion and air closure spatial. In addition, the combination of these two technologies is perfect to cover mixed environment because air closure spatial is based on Google Street View images, so it's perfect for outdoor application. Instead, structure from motion is based on a set of unordered images used to localize the user, and so it's perfect for any kind of private or indoor spaces. About the path planning, we studied, like in the previous case, the state of the art, and so we understand that the problem is all about how the space can be modeled. We have solutions that model the space and in particular the path ex ante, like for example the one that applies offline learning and line following. The last one in particular requires the installation in the environment of lines that can be followed by a vision-based system. In the second group, so the solution that computes the path on demand, so after a specific request by the user, we have some sensor-based solutions like the one that apply UWB and BLE, so they requires a preparation of the environment. These issues is overcome by SLAM-based solutions that, on the other hand, requires the user to wear heavy equipments. So we have more lightweight solutions like the one that apply 2D CAD map, but as you can understand, we have a ground-only representation of the space. So the most promising solution is the existing works that apply building information modeling, because the model exists for our purpose, and so we can apply the knowledge that comes from that modeling for computing a path after a request provided by the user. So what we did is, given these premises, so isolated these technologies, think about a possible integration of computer vision-based user tracking and BIM-based path planning to define a navigation assistant for blinds that can work in mixed and unprepared environment. We did that by considering the selected technologies and defining this system architecture. As you can see, it is based on three main blocks: the Google Cloud Platform, that you can see here, based on their closure spatial, the custom cloud platform, based on structure from motion and BIM. So the Google Cloud Platform provides user tracking, the custom cloud platform provides user tracking and also path planning. In addition, we defined the third block, that is the Audio Augmented Reality Navigation Assistant, conceived as a smartphone-based application. We selected for this application the Audio Augmented Reality technology because it is intuitive and not intrusive. Intuitive because it allows the user to follow the sound, because the audio source is consistent with the message. It means that if the directions is turn right, the user will effectively hear this direction coming from the right. So the decoding effort is lower, for example, than other technologies like, for example, haptic-based solution. It is non-intrusive because it is based on a vocal communication with the system. So this is a hands-free system, and this allows the user to combine this kind of solution with other navigation aids, like for example, traditional ones, like white canes or guide dog. So let's start with the description of the system architecture. The first model, as I said a few seconds ago, is the Google Cloud Platform based on their Coder Spatial. The interface with the rest of the system architecture is based on their Coder Spatial API. This module, so the overall engine is based on the visual positioning system, VPS, provided by the Google service. It is based on Google Street View images that are used to define a point cloud of the space used as a reference to localize any full query image provided as a query. So the position and orientation of the device and so of the point of view of the user can be retrieved. As you can imagine, Google Street View images are not available everywhere. So where we don't have this kind of data, we have to combine the system with other solutions. And this is why we integrated the previous one with a custom cloud platform we developed internally in our research group. Here we have the image-based registration engine that is based on a structure from motion pipeline. It means that we use technologies like, for example, ColdMap and HFNet to build a mapping of the environment based on a set of unordered images that are collected just one for the environment. The result is a sparse point cloud that you can see reported here that can be used to perform a 6 degree of freedom localization of the image, so define the position and orientation of the device based on HFNet and the perspective and point algorithm that return the pose and orientation given a matching between 3D points in the point cloud and 2D points in the image. The custom cloud platform, as I mentioned, includes also the path planning engine to compute the reference path to the destination. We implemented it using a headless Unity 3D interface based on high-performance libraries like GLTFast and Draco. This is a BIM-based space modeler because it imports the BIM as a GLB, so the data storage store the FC, and includes also a function that can transform the IFC into the GLB that is more performing. In addition, we have also the Pathfinder that is able to compute the path from the starting point to the destination. The starting point is provided by the user tracking task. Instead, the destination is the result of a combination of queries, like the EQL queries performed in the data storage. We use this kind of query, so EQL, because we selected as a graph database ArangoDB based on this language. And the query we perform is the one that returns, given a building information model, the list of room described by, as you can see here, the global unique identifier and the name of the room. These informations are then applied within the space modeler by an OpenAI module that is able to select the global unique identifier whose name match the request of the user. For example, if the user says, "I'm hungry, please give me direction to the fridge," the OpenAI model can understand that the destination we are looking for is the kitchen. The same if you are looking to the bedroom, or if we are providing more direct requests, like for example, "Please take me out of here." The system is able to understand that we are looking for the entry hall. I mentioned the OpenAI model, but we can apply any other kind of AI API to be integrated in this system. So finally, we have the Audio Augmented Reality Navigation Assistant module. As I mentioned, it is based on the AAR. We have yellow boxes that are the hardware components and the white boxes that are the software components. So we have the microphone and the speakers that define the communication interface between the user and the system, the camera and the location service sensor that provide the input for the user tracking, and then we have the AI speech-to-text intent, registration manager, path follower, and AAR synthesizer I'm going to describe. So the functioning can be summarized in these ways. So the user provides a request, an audio request. The AI speech-to-text intent understand if there is the intent to navigate or if it is a general request. If there is the intent to navigate, the audio request is translated to a textual request, as the one I mentioned in the previous slide. So the textual request is now provided to the registration manager that can return based on the three engines I described in the previous slide, the pose and the path. So the 6 degree of freedom pose of the user and the path to a given destination. The registration manager at this point can transform the pose and the path into the coordinate reference system of the navigation assistant and transmit them to the path follower. The path follower is based on the line of sight algorithm, and it is able to provide the correction angle, so the angle that can adjust the user trajectory to the reference trajectory to reach the destination. At this point, the correction angle is compared to a list of correction angle ranges to return the direction we have to provide to the user to adjust the trajectory. And at this point, we have the main function that is provided by the AAR synthesizer that will place an audio source, a virtual audio source, in the developing environment, that in our case is Unity, in correspondence of the direction of next point to reach. In this way, the user will hear the direction coming from the same place. So, as I said before, if the message is turn right, she will hear the message coming from the right, and so on. So at this point, we executed experiments to test the effectiveness of the proposed system. We used the Xiaomi 13 Pro smartphone, where we start our application, and the Ray-Ban Meta smart glasses with embedded speakers for a smoother experience during the experiments. We selected as a case study our university, so the Università Polytechnic delle Marche, and in particular the Faculty of Engineering. We classified the experiments we conducted into two parts. Part one, that is a stationary part of the experiments related to path planning, and the second part that is in motion experiments, so we tested the user tracking and the path following. Starting with the path planning, so the first part, we provided a request to the system, like for example, I have a lecture in classroom 140/3, how can I reach this room? The result is the name of the room, and in particular the global unique identifier that can be used to return the geometric center of the room. This is set as a destination in the system, and as you can see, we have the path in green to the desired room. Here we reported the coordinates of the reference paths that are used to are used in the following steps, so are used for the user tracking and path following. We repeated this kind of test for all the classrooms or level 140 in our university. As you can see, all the path planning tests have been successful, so all the green line reached the desired classroom. I have a couple of considerations. The first one is that if the room has more than one door, the system is able to provide the path that is across the closest door, so it ensures the shortest path. Another consideration is about the first one and the second one of the experiments. As you can see, the green line is across another room that in a general case can be inaccessible or occupied. So this is why we think that next study should focus also on considering building semantics to avoid this kind of scenario, so to be aware that the path will be across common area and not, for example, classroom or other kind of rooms in the same situation. So about the part 2 of the experiment, so about the user tracking and path following task, we selected one of the previous rooms, so classroom 140/3 as a destination. The experiment involved, in this case, 20 users, ranging in age between 19 and 45 years old. Each test involved the application of the developer system, and each user was asked to repeat the test twice. In the first case, in blindfolded condition, and in the second case, in sighted condition, to provide a benchmark to be used in the analysis of the results. Before the execution of the test, we checked that in the area, in the outdoor area, we have the Google Street View service, so we have the images shown here. For the indoor area, we collected a set of unordered images, and as you can see in this clip, we built the sparse point cloud, so we built the 3D mapping to be used as a reference for the 6th degree of freedom localization. So I reported here an extract of the experiments. This is me that is navigating in this part of the path. And as you can see here, I reported the screenshot of the application. We have the correction angle that is computed in real time, so as the user is moving. And according to that, the system provides the direction. So, for example, turn slightly right, go ahead, and so on. You should hear also the audio, and wearing the earphones, you will hear the direction coming from the same destination.
Turn right. Go ahead.
This is another extract of experiment, in this case indoor, in this part of the path. So same functioning, correction angle computed, and the direction provided in real time. So the data collected during the experiment have been processed and provided as a result. So we built this chart to describe the performance of the system. Here we have the trajectory comparison in blindfolded and sighted condition, and here the trajectory analysis in blindfolded and sighted condition for the 20 users involved in these experiments. So let's see more closely one of the charts. About the trajectory comparison, we have the comparison between the reference path in orange and the user trajectory in blue, both in blindfolded condition and sighted condition. First of all, as you can see here, the pattern of the path in blindfolded condition is pretty similar to the one in sighted condition. It means that the behavior of the user in blindfolded condition is pretty similar to the behavior of a user that can see the environment. I reported here in red the maximum divergence between the reference trajectory in orange and the user trajectory in blue. It is about 1.5 in both cases, and so this confirmed the good performance in this scenario of the navigation assistant. Another consideration is about the position in which we notice the maximum divergence. So it corresponds to curved sections, and it is the same for the other test. This can be explained by considering the fact that when a user hears the message like turn right, there are a couple of seconds in which the user tends to diverge from the reference path, and then the message will apply the correction, and so it will be in line with the reference path. This is confirmed by the trajectory analysis charts, in which we noticed a correlation between the local divergence reported in green and the heading variation, so the curvature of the user during the experiments. This confirms what I said before. So when there is a change of direction, there are a couple of cycles in which there is an adjusting time. Another important consideration regards the average divergence between the user trajectory and the reference one. In this case, we have a lower average divergence compared to the one in sided condition. So it means that the user in the blindfolded condition tends to follow the reference path more closely than to the sided one. It is confirmed by a statistical analysis we performed, in which we noticed that the mean values of the maximum divergence and the average divergence in blindfolded condition are lower than in sided condition. In fact, the average divergence is below a real scale threshold we selected in 100% of cases. The threshold we selected is the 60 centimeters of the shoulder width. Instead, in the sided condition, the average divergence is below that threshold in 75% of cases. This is why when the user is able to see the environment, she tends to adjust the trajectory according to their personal experience. So just to conclude, what I present is an augmented reality navigation assistant that, thanks to the adopted technologies, can provide a support to blind people in mixed and prepared environments. So we expect that a similar system can effectively enhance the independence of blind people because it does not require any kind of physical infrastructure. It works indoors and outdoors. And in addition, thanks to the application of the audio augmented reality that is, as I said, intuitive and not intrusive, it is compatible with other tools that can provide, for example, obstacle detection, like the most simple, that is the white cane. A limitation of the study is that it requires the existence of Google Street View images, or at least a set of unordered images provided by the user for the first time. We have a good expectation about the possibility to overcome this because the percentage of digitalized build asset is increasing. So we expect that all the assets will be digitalized soon. About future studies, instead we will focus on the possibility to improve, as I said, the route quality, avoiding the cases in which the computed path is within rooms that can be inaccessible or occupied, like the classroom I mentioned before. In addition, we would like to develop a better method to deliver the correction angle, avoiding that kind of divergence in correspondence to the curve section. And finally, of course, as future developments, we will test the system in different scenarios, involving in the experiment, if possible, also blind and visually impaired people to have their precious feedback about the proposed system. So I reported here the reference I mentioned across the presentation, and thank you very much for your attention. I'm available for any kind of question and curiosity. Thanks.